Welcome, everyone. Thank you for joining me today. I'm excited to introduce our topic, the AI monoculture. This presentation is an evidence-based briefing on synthetic data, systemic risk, and the future of secure development. Over the next few minutes, we'll explore how these elements are shaping our technological landscape and what it means for us moving forward. Let's get started. G-Notebook-LM is highlighting a very urgent and emerging reality that we need to address immediately, both from a governance and technical standpoint. One of the key issues here is the expanded attack surface. As AI systems become more integrated, new vulnerabilities like prompt injection are not just theoretical, they are practical, real threats that can be exploited in production environments. Then there's the problem of model degradation. When we train AI on its own synthetic outputs, we risk creating a feedback loop where the quality and reliability of the model decline over time. This phenomenon is often called model collapse and can seriously undermine trust in these systems. Another critical point is correlated vulnerabilities. A single exploit can potentially compromise many systems that are built from the same AI patterns. Shared bugs and vulnerabilities can spread at an unprecedented scale, making the entire ecosystem more fragile. This concern is echoed by AI engineers who warn about a growing monoculture, where many models share the same logic, bugs, and weaknesses. Independent, peer-reviewed research supports this warning, confirming that these issues are real and pressing. Finally, I want to emphasize that our rapid adoption of AI for coding and other applications is creating systemic risks. While AI offers incredible opportunities, it's also making our systems more fragile if we don't take proper precautions. So, understanding these vulnerabilities and risks is crucial as we move forward in integrating AI more deeply into our systems and workflows. Let's take a closer look at some of the new security threats we're facing with Notebook-LM. Prompt injection and reverse engineering are practical exploits that can be weaponized, meaning they can be used maliciously to manipulate or extract sensitive information from models. Additionally, we see how bugs can propagate through AI-generated code, spreading similar vulnerabilities across multiple projects and organizations. Another major concern is model data provenance. Since these models are trained on publicly available data, it creates feedback loops and raises legal and technical issues around data ownership and quality. Then, there's the issue of code monoculture. Because large language models tend to reuse common public code patterns, many systems end up sharing the same logic structures, which can amplify systemic vulnerabilities. These points were raised by AI engineer Sharad Gupta, and they sparked our investigation. We wanted to go beyond just taking these claims at face value, so we set out to empirically validate these observations with real-world evidence. This approach helps us better understand the risks and challenges we're facing as we develop and deploy these powerful tools. All right, let's dive into slide 4. Here, we're focusing on the degradation process that can occur in generative models over time. When a model generates content, whether it's text or code, that content can end up being published publicly, like on the web. This is the publish step, where the content becomes accessible. Next, web scrapers can pick up this published content and feed it back into training pipelines, which is the re-ingest step. This creates a cycle where the model's own outputs are used as training data, which can have some serious implications. In fact, experiments by Shumilov and colleagues in 2024 have shown that this phenomenon, this feedback loop, is real and empirically validated. It's a core mechanism behind systemic risk in AI systems. Then we come to the generate phase, where an LLM, or large language model, produces synthetic code and text. This is the core capability of these models, creating new content based on what they've learned. Finally, we reach the degrade stage. Over time, as models repeatedly generate and re-ingest their own outputs, their quality, diversity, and connection to ground truth data diminish. Essentially, the model's outputs become less accurate and less varied, which can lead to what we call model collapse. This feedback loop can cause a measurable decline in performance, and understanding this process is crucial for managing the risks associated with deploying large language models. Let's take a closer look at the evidence supporting the security concerns around AI tools like GitHub Copilot. Empirical analyses have shown that there are non-trivial rates of insecure code being generated. This means that, in real-world scenarios, AI is often reproducing unsafe coding patterns that it has learned from public repositories. This reproduces a key issue. When developers rely heavily on AI suggestions without thoroughly vetting the code, it can lead to the propagation of vulnerabilities across the entire ecosystem. Essentially, the AI isn't just helping with productivity, it can unintentionally spread security flaws. For example, a classic case is SQL injection vulnerabilities. You might see code like this, where a query is constructed by concatenating user input directly, such as select from users where sum equals plus username plus. This is a well-known security risk because it opens the door for malicious input to manipulate the database. When AI suggests code snippets like these without proper safeguards, it contributes to a cycle of insecure coding practices. The productivity gains we get from these tools are significant, but there's a hidden cost: the increased likelihood of introducing and spreading security vulnerabilities at scale. So, in summary, while AI assistants like GitHub Copilot can boost productivity, they also have the potential to propagate insecure code widely, which is a serious concern for software security. On this slide, we see that security researchers have demonstrated quite high success rates in extracting internal prompts and uploaded files from live, custom GPT instances. This highlights a significant vulnerability in these systems. Essentially, it shows that internal data, which should be protected, can be accessed through certain attack methods. Furthermore, OWASP, the Open Web Application Security Project, now lists prompt injection as one of the top 10 risks for large language model applications. This is a big deal because it underscores how serious this threat has become in the cybersecurity community. What this all points to is that the prompt itself has become a new and exploitable attack surface. In other words, the way prompts are designed and used can be manipulated by malicious actors to bypass security measures and cause harm or extract sensitive information. This emphasizes the importance of understanding and addressing prompt security, especially as these models become more integrated into critical applications. It's a reminder that as we develop more advanced AI, we also need to stay vigilant about potential vulnerabilities. Now, let's take a closer look at the convergent failure point. Essentially, because many systems share common logic, libraries, and vulnerability patterns, a single exploit can actually impact multiple systems at once. This means that a vulnerability isn't just isolated. It can have widespread consequences across different platforms that rely on similar components. Moving on to human oversight erosion, as AI tools become more integrated into our workflows, there's increasing pressure to prioritize productivity. This often results in less time spent reviewing outputs, which unfortunately allows low-quality or even insecure AI-generated code to slip through and be merged into production. It's a critical point because human oversight is still our best line of defense. Next, we have algorithmic pattern amplification. Large language models tend to favor high-probability patterns, and this reinforcement can lead to very homogeneous outputs. While that might seem efficient, it actually stifles diversity and creativity, making systems more predictable and potentially more vulnerable to exploitation. Finally, there's the issue of unvetted data ingestion. These models are trained on vast and diverse datasets, often including web-scraped content. This creates a feedback loop where AI-generated outputs are re-ingested, which can reinforce existing biases or vulnerabilities and make the system even more susceptible to systemic risks. All of these drivers, shared logic, oversight erosion, pattern amplification, and data feedback, are interconnected and contribute to the broader picture of systemic AI risk. Recognizing these points helps us understand where we need to be most vigilant. Let's take a closer look at some of the potential risks that could impact the stability and reliability of general-purpose large language models over time. We're talking about the concept of model collapse, where these models might experience systemic degradation, leading to a decline in their performance and usefulness. This is especially concerning as we see stagnation in AI progress for tasks that require factual grounding, meaning the models might become less accurate or less reliable when it comes to providing factual information. Another critical point is the increasing cyber risk due to monoculture vulnerabilities. When many models rely on similar architectures or data sources, a systemic cyber event could have widespread consequences, making the entire ecosystem more vulnerable to attacks. Looking further out, over the long term, say 5 to 7 years or more, we could see the emergence of the first major incidents involving correlated software failures. These are failures that aren't isolated but are interconnected, potentially causing large-scale disruptions. Additionally, as models are retrained, they may inadvertently ingest degraded synthetic content, which can further deteriorate their quality over time. Regulatory and compliance scrutiny is also likely to increase, adding another layer of pressure on how these models are managed and deployed. In the medium term, say 2 to 5 years, we might observe a measurable increase in vulnerabilities within AI-assisted coding tools. This could lead to more frequent prompt-style exploits on chatbots and integrated systems, which attackers could exploit more easily. Additionally, we're already seeing a rise in low-quality AI-generated content flooding the web, which could impact information integrity and user trust. In the short term, think 6 to 24 months, we're already seeing efforts like GNotebookLM, but it's important to recognize that these risks are compounding. The overall impact over a 7-year horizon could be significant, affecting everything from model reliability to security, regulation, and content quality. This is a complex, evolving landscape, and understanding these timelines helps us better prepare for the challenges ahead. Now, let's talk about how we can actively defend the new prompt-level attack surface. This means implementing robust security controls that are designed specifically to address these emerging threats. It's crucial to integrate security into every stage of development, which is why a secure development lifecycle is so important. Another key point is to treat all AI-generated output as untrusted by default. We can't assume that the output is safe without verification, so establishing strict controls around this is essential. Controlling our training data supply chain is equally vital. We need to ensure that our data sources are secure and reliable, because the quality and integrity of our data directly impact the safety and fairness of our models. This all ties into the broader concept of data and model governance. Managing how data is collected, stored, and used helps prevent vulnerabilities like AI monoculture, which poses significant risks. The risks are real, but by adopting a deliberate, multi-layered strategy, covering the entire lifecycle of data, models, and code, we can substantially mitigate those risks. Finally, as we look ahead, tools like GNotebookLM can support this strategy, guiding us toward greater AI resilience. So, in essence, this slide emphasizes the importance of layered security measures, vigilant governance, and thoughtful control to build a safer, more resilient AI environment. Let's start by talking about filter ingestion pipelines. This is all about deploying retrieval filters that actively block or label content that is likely to be model-generated. The goal here is to prevent this type of content from being used in automated retraining pipelines, which helps maintain the quality and integrity of our training data. Next, we need to consider curating critical datasets, especially for sensitive domains like finance, healthcare, or critical infrastructure. In these cases, relying solely on public web scrapes isn't sufficient. Instead, we should use vetted, licensed, high-quality corpora, ensuring that the data is both reliable and appropriate for the domain. Then, implementing provenance metadata is crucial. We must mandate content provenance tagging for all data used in training. This includes identifying whether the data has been human-verified, generated by AI, or its source. Maintaining immutable audit trails ensures transparency and accountability throughout the data lifecycle. Finally, I want to highlight GNotebookLM, which supports Pillar 1, building a high-integrity data and model supply chain. This approach emphasizes creating a trusted, traceable system for sourcing and managing data, which is fundamental for maintaining the integrity and reliability of our AI models. All these elements together help us build a robust, trustworthy foundation for AI development. Let's talk about enforcing human-in-the-loop, or HITL, as a critical part of embedding security into the AI development process. This means that for any high-risk or production-facing outputs, such as critical code, infrastructure configurations, or documentation, we require explicit human approval before they are finalized. This step ensures that humans remain in control and can catch potential issues that the AI might overlook. Next, diversifying our models and architectures is essential. Relying on a single model or a single vendor can introduce risks like monoculture effects or correlated failures. By using ensembles of different models or architectures from multiple vendors, we reduce these risks significantly. This approach increases robustness and helps prevent single points of failure in our AI systems. Finally, implementing zero-trust verification is non-negotiable. Every piece of AI-suggested code must pass through static analysis, or SASD, along with thorough unit tests. Plus, a mandatory security review must be completed before any code gets merged into our main codebase. This layered approach acts as a final security gate, ensuring that only safe, verified code is deployed. Together, these practices, human oversight, model diversification, and rigorous validation, form the backbone of embedding security deeply into our AI development lifecycle. They help us build more trustworthy, resilient systems that align with our overall security goals. Now, let's look at the next step in securing our LLMs by updating enterprise threat models. It's important to formally consider LLMs as first-class attack surfaces during your security assessments and red teaming exercises. This means treating them as critical points of vulnerability, just like any other system component, and thoroughly testing for potential exploits. Moving on to deployment, implementing prompt defenses is essential. This involves deploying tools like prompt injection detectors and known answer checks, which are recommended by security frameworks such as the OWASP Top 10 for LLMs. These defenses help prevent malicious prompts from causing harm or leaking sensitive information. Another key aspect is isolating and sanitizing inputs. We need to treat all user-provided input to LLMs as potentially malicious. That means sandboxing LLM integrations and applying strict input and output controls to prevent data leakage or other security breaches. Overall, this pillar, deploying next-generation security controls, is about proactively managing risks and making sure our LLM deployments are as secure as possible, aligning with our broader goal of responsible and resilient AI usage. Let's talk about some key measures we're implementing to improve AI safety and integrity. First, we're halting automated retraining pipelines that rely on unvetted web content. This is crucial because we want to ensure the data used for retraining is thoroughly checked and trustworthy. Next, we're mandating provenance metadata for all retraining data, clearly marking whether it comes from human sources or AI. This transparency helps us track data origins and maintain accountability. We're also enforcing mandatory static and dynamic code checks on 100% of AA-suggested code before it gets merged. This step is vital to catch any issues early and prevent vulnerabilities from slipping through. In addition, we're adding prompt injection tests to all penetration testing and red teaming scopes. This helps us identify and defend against potential prompt manipulation attacks that could compromise the system. To avoid over-reliance on a single vendor, we're launching a model diversity initiative. This promotes a broader ecosystem and reduces dependency risks. Finally, we're funding cross-industry monitoring to detect emergent monoculture indicators, which can pose security and resilience challenges. All these steps are part of our broader effort to keep AI safe, reliable, and resilient in a rapidly evolving landscape. Let's take a closer look at some of the key evidence that shapes our understanding of AI risks. First, there's a study by Shumilov and colleagues from 2024 which shows that AI models can actually collapse when they are trained on recursively generated data. This highlights how fragile some AI systems can be under certain training conditions. Then we have a report called Security Weaknesses of Copilot-Generated Code in GitHub, which was published on RZiv and ACM. It points out vulnerabilities in code generated by AI tools like Copilot, emphasizing the security risks involved. Next, Liu and his team in 2023 examined prompt injection attacks against applications that use large language models. This kind of attack can manipulate the model's output, raising concerns about security and trustworthiness in AI-driven applications. Additionally, Spenneman's 2025 work delves into quantifying AI-generated content on the internet. Understanding how much content is AI-produced helps us grasp the broader impact and potential misinformation risks. Now, moving on to open questions, one major area is mitigation efficacy. While strategies like provenance tags and adversarial training show promise, we still need more real-world testing to truly understand how effective they are outside the lab. Another important point is risk heterogeneity. Not all models pose the same level of risk. Architectures, deployment contexts, and use cases vary widely, so a one-size-fits-all approach doesn't work. And finally, there's the legal and liability landscape. The rules around training on public data and who's responsible for AI-generated errors are still evolving, making this a complex area for policymakers and developers alike. All of these points connect back to our overall theme: understanding and addressing the foundational uncertainties in AI safety and security. The warnings about a growing AI monoculture are not just alarmist fiction. They are rooted in real, documented technical risks and active research findings. What this means is that without intentional governance, rigorous verification processes, and diversity in AI architecture, our entire AI ecosystem could face serious consequences. We risk encountering degraded model quality, an increase in insecure code, and more attack surfaces that malicious actors can exploit. The key takeaway here is that the time for strategic intervention is now. We can't afford to wait or assume these issues will resolve themselves. The evidence overwhelmingly shows that this is a real and systemic risk, one that requires our immediate attention and action. This connects directly to the overall theme we've been discussing: the importance of responsible development and diverse approaches in AI. If we don't address these risks proactively, we could undermine the stability and security of AI systems that are becoming increasingly integrated into our lives. So, it's crucial that we act now to steer the future of AI in a safe, reliable direction.